Now that we're familiar with the structure of a binary search tree, let's look at some of the operations we can perform, starting with search. Let's use a recursive approach to our function, where we define a function, find, that creates subproblems by repeatedly calling on itself until the solution becomes trivial. There are 4 cases that can occur when we call find on a node. First, if the target value, in this case 25, is less than the value in the node, root, that we are searching at, we know that our target node must be located in the left subtree. Knowing this, we can call find on the left child of root, reducing our problem space to nodes in the left subtree, similar to how we can cut the search space in half using binary search on an array. Notice that we are returning the result of our recursive call to find. This is the underlying assumption of recursion. We assume that somewhere along these future calls, we will find the answer to the problem, and in this case, we will just return that answer. Now that we call find on the left child, the node containing 20, we can see an alternate case. Here, the target value, 25, is greater than the value stored at the root, so we can call find on the right child, since our target must be in the right subtree. Finally, we have reached a node containing a value that matches our target. This is our third case, and one of the trivial cases we discussed earlier that concludes recursion. Here, we can simply return the value since we found what we were looking for. There is a fourth case, however. What should we do if our target value is not present in the tree? Let's instead pretend we are searching for the value 26. At the node 25, we would call find on the right child since 26 is greater than 25, but this child is empty. So for our final case, we can say that if we reach a node that is null or contains none, we will simply return this null value as an indicator that our search operation failed. We can organize our code into 2 overarching cases. The base case, where the solution becomes trivial and we return said solution, and the recursive case, where we would like to break the problem into subproblems for efficiency, resulting in a recursive call to the same function. In this example, our recursive case used conditionals to figure out the best way to navigate the tree to meet our goal of finding a specific value. But what if we had a different objective, like finding the maximum value of the tree? The max is the rightmost value of the tree. That is, it is a node found by traveling along the right branch of the tree until there is no more right child. Think about how we can adapt the recursive case of this method to achieve this goal, as functions like finding the min or max of a tree can be quite useful, as we'll see when we're developing our other operations.